Hey everybody, John here. In this video we're going to talk about natural logarithms, and then we're also going to do a little bit with applications, and then we'll finish up this lecture in the last video talking about some of the properties that logarithms have. So a natural logarithm is just one where the base of the logarithm is e. So what I didn't mention in previous videos is that if you have log base 10, which is called a common logarithm, so let's say I just have log of x. When you don't have anything written here, it is assumed that that base is 10. So if you don't write anything, it's assumed it's 10. You can still write the 10 if you want to, but you don't have to when it comes to 10. Just like with a square root, you don't have to write the 2 when you're doing a square root. You only have to write a number if it's something other than a square root. If there's nothing here, people just assume it's a square root. So a common logarithm is this base 10, but base e comes up so often with logarithms that instead of having to write log base e every time, we came up with this notation ln of x. Again, I didn't come up with it. It was it was actually a French guy, and that's why it's ln instead of nl, because it's logarithmic natural, or it's I don't have a French accent. I'm sorry, but it's the adjective comes after the word instead of in front of the word in French. So that's where this comes from. So anytime you see ln of x, you're thinking all the same things. What do I raise a number to get this? But the number, when you see this notation, the number that you're raising an exponent to is always e. So when I see ln of x, I don't say ln of x. I don't think in my head natural log of x. I think, oh, what would I raise e to get this number? So looking here, this is saying, what would I raise e to? What would I raise e to get e to the fourth? And hopefully you're seeing that, oh, well, if I have e to the something and e to the fourth, then that something has to be 4. What would I raise e to get e to the fourth? Well, I would raise e to the fourth to get e to the fourth. What would I raise e to get 1 over e to the 2.5? Well, that would be negative 2.5. What would I raise e to get 3? Well, remember that e is about 2.71828. And so it would definitely be bigger than 1. So e to the 1 would be 2.7. E squared, let's see, e squared is probably it's less than 9, because 3 squared would be 9, but it's 7.389, so it's a little bit bigger than 7. So raising e to an exponent and getting 3, that exponent definitely has to be between 1 and 2, and I'm thinking probably closer to 1, so 1 point something. Okay, and so I would have to I'd have to put this in my calculator. Now remember where we went on the calculator to put in e to some power. It's 2 buttons above on. It has an ln right on there, so you just press ln of 3 and then hit enter, and we get 1.098, well, 9 if you round. And so like I said, I highly recommend that when you're doing these problems that you are doing this sort of guesswork in your head where you're thinking, oh, I'm raising e to some power and getting 3. So my answer should be something between 1 and 2, closer to 1, because 2.7 is closer to 3 than 7.3 is. And that's what I get when I do e to the 1, I get 2.7. When I do e squared, I get 7.4, and so I knew it was going to be somewhere between 1 and 2, but definitely closer to 1 as an exponent, which is exactly what happened. And I recommend doing that reasoning just so that when you're getting answers out of these problems, if you're getting an answer that doesn't seem right, you should have an idea of what it is in your head beforehand. And if you're getting something that doesn't seem close, then at least you have a check to sort of back up and say, oh, maybe I typed it in my calculator wrong, or maybe I just wrote the problem down wrong. I don't know. Maybe I did one step, I did some division wrong. But you should have some idea of what the answer is going to be in your head before you continue. All right. So that's natural log. So let's talk about Newton's law of cooling. This is an application problem, and it actually looks very similar to exponential growth and decay, because that's exactly what this is. And if you remember, that was this formula. And so this is very close, where A of t is sort of this difference between the outside temperature and the surrounding temperature and the temperature of the object initially. But then we do have sort of this extra piece here. And you'll notice that because the temperature is always decreasing in most of these cases, we have this negative in the exponent built in because we're assuming decay. All right. Now you don't have to come up with this equation itself in any of the problems that I give you. I just want to go through this with you. So I don't know if you follow what happened years ago. There was this lawsuit against McDonald's because somebody ordered hot coffee and took the top off and put the coffee between their lap, and then it spilled and it burned them. And so McDonald's has a lot of reason to be wanting to know about Newton's law of cooling, so that they know that they're giving people coffee at a temperature that is desirable, and in this case that is 125 degrees Fahrenheit. Now that's probably just made up for the sake of this problem, but what they know is that when you take the coffee from the coffee maker, whose contents are 180 degrees Fahrenheit, so that's the initial temperature of the coffee. After 1 minute, the coffee cools to 165, and we know that the room temperature is 72. So we have a lot of information here. But looking back at this equation, let's write it down. So T equals T sub S, which is the surrounding temperature, plus, and now we have the difference between the original temperature of the object and the temperature of the surroundings, and then we have this e to the negative kt piece. Okay? Now, in order to answer any questions about this particular cup of coffee coming from McDonald's, I need to know this K value. And so that's actually going to be the first thing that I try to solve for here. So I know that T, for this particular problem, T equals 72, that's the temperature of the room, plus the difference between the initial temperature of the coffee, which is 180, minus 72, that's 108. And then we have e to the negative kt. Okay, so I filled in everything that the problem has told me so far. So I'm going to use this 165 and the fact that that happens 1 minute after. I know that after 1 minute the coffee is 165 degrees. So I know that the temperature, the current temperature of the object, which is what T is equal to 72 plus 108 e to the negative k times 1, or 1 minute. So I plug the 1 in for time because that's 1 minute, and I know the temperature after 1 minute is 165. This all came from the problem. So I need to solve this equation. I need to solve for k, but k is in the exponent. So what I'm going to do to solve for k, which is in the exponent, is I'm first going to move everything away from the thing that has the exponent variable in it, which is e to the something. I'm going to move everything away from e to the something that I can. So the first thing I'm going to do is subtract 72, get this 72 out of there. So we have 165 minus 72, which is 93. And that equals 108 e to the negative k. I'm not going to keep writing the 1 because k times 1 is just negative k. But before I can get to this exponent, I need to get rid of this 108 here because that's not being raised to an exponent. So now I'm going to divide by 108 on both sides. So divide by 108. So I have 93 over 108, and I don't know if that reduces. I'm going to put it in my calculator and then hit math fraction. And it does reduce to 31 over 36. Okay, but that's not the important part. The important part is now I have e to the negative k. So now I want to solve for this exponent. This is where the logarithm comes in. Okay? So there's two ways you can think about this. I can use the definition of a logarithm, which I've written on top of almost every slide. Log base a of x is the same thing as a to the y equals x. So I can do this and rewrite it as a logarithm. So in that case, I would get negative k equals log base e of 31 over 36, which is saying negative k equals ln of 31 over 36, because natural log is log base e. And then if I wanted to get k totally by itself, I would just multiply both sides by a negative 1. And this would be my exact answer written as a logarithm, as a natural logarithm. And Pearson's going to ask you to write your final answer in terms of natural logarithms. So this is how you would write your answer. Okay. The other way I can think about this is I can, you know how, let's say I had 31 over 36 equals 2k, right? To get k by itself, I divide by 2 because right now it's being multiplied by 2. Or even if I had k to the e, I could eth root both sides. I could raise both sides to the 1 over e power. I can undo what's there to try and get to my variable. So I can perform the same operation to both sides of an equation. So we can think of natural log as an operation, and if I ln both sides of the equation, ln of 31 over 36 equals, well, what do I raise e to get e to the negative k? The answer is negative k. So the ln and the e cancel out. They're inverses. So I get negative k, and then I can solve for k by dividing by negative 1. So I'm going to get the same answer either way. And then if Pearson asks you for the answer as a decimal, the answer would be k is equal to 0.1495. So if they wanted you to round to 3 decimal places, it would be 0.150. Okay, so now that I have my k value, I can answer the question, because I know that t equals 72 plus 108 e to the negative 0.15 t. And so if I want to know how long it takes to get to 125, I would plug that in. And I would go through pretty much this whole process that I went through, this whole process here, or this process here, however you feel more comfortable. But instead of trying to find k this time, what I'm trying to find is t. So I have everything else. So I'm going to subtract 72, I'm going to divide by 108, I'm going to ln both sides, and then I have to divide by negative 0.150 to get t totally by itself. Now I want you to try that on your own, and at the beginning of the next video, I will go through that process and give you the correct answer. I will see you in the next one.